Welcome to the Chemistry, Biology and Math Revision Hub. Today we are doing the Pearson Edexcel International A-Level Chemistry Unit 5 for June 2023. Let's begin with the first question. Question 1. The equation for a redox reaction is shown. So this is the redox equation they're talking about. They say what is the cell diagram for this reaction. If we look at this reaction given, we can see this is being converted into that. This is an oxidation reaction, and we see copper 2 is being converted to copper, that is reduction. Since the vanadium half cell has two different oxidation states and there is no vanadium, so we cannot use vanadium as an electrode, we need to use platinum. So platinum is going to be first, which is a solid. And then we see a phase separator. This one is to separate the phases between solid and aqueous. However, because we have two aqueous ions, they're separated by a comma. And then there is a salt bridge to separate the two half cells. And to the other side, the most oxidized version is going to be closer to the salt bridge, which we see here, and then the reduced version to the other side, so the answer should be a D. In question 2, some standard electrode potentials are shown. We have the table here. They say what reaction is thermodynamically feasible. So we look at all reactions actually and made it simpler. We can see for this equation A here, we can see these are the reactions. Since cerium is being converted to cerium 3+, this is going this way and the other is going the other side. However, this is more negative than that and it should favor the other direction, so that reaction will not be feasible. When we go to B, we can see this is being converted to that and that. So we should be coming from this side to this side. And for this one, it's going to be converted the other side. We see this is more negative than that. This should be the other side for feasibility to occur, so that will also not be feasible. You could also calculate the E theta for the cell. You'll see that for B, it's going to be negative. Going on to C, manganese 2+ being converted to manganese 3, as well as manganese solid. This is going to be what we have here. To convert manganese 2 to manganese 3, this should be coming in this direction. And to convert manganese 2 to manganese solid, it should go in the other direction. But this is more negative, so the reverse reaction should be true. It should be going in that direction, as this goes in the other direction for feasibility to occur. That means C is not going to be feasible. And finally, we look at D, which is what we see here. Because magnesium is being converted to magnesium 2+, that is going to be going the other direction. And cerium 4+ is being converted to cerium 3+, again going in this direction. We see this is going to be feasible, because the one with the more positive electrode potential is going in the forward direction, while the other is going to go to the other side. So that will be my answer. It's the only one that is going to have a positive E theta for the cell. In question 3, in a chemical reaction, the E theta for the cell is directly proportional to. It's going to be directly proportional to the total entropy change based on these equations we have here. So D should be my answer. In question 4, for the reaction shown, we see E theta for the cell is equal to positive 0.89 volts. They've given us the equation here. They say, which statement can be deduced from this information only? From here we can see this is being converted to that, and that is oxidation. They say the reaction will not occur under any conditions. We cannot deduce that from here. And again, you can see this is positive, so it means the reaction will occur, so that's wrong. The reactants are kinetically stable with respect to the products. It's not true, because kinetic stability is going to be related to the activation energy. The reactants are thermodynamically unstable with respect to the products. This is true because a reaction will occur at standard conditions, so we can see it means the reactants are less stable in comparison to the products. So this should be the answer. In question 5, which reaction occurs at the negative electrode in the hydrogen-oxygen fuel cell? Remember, the negative electrode is the anode where oxidation occurs. This is the only equation that is going to occur, and actually it occurs in alkaline conditions at the anode in the hydrogen-oxygen fuel cell. In question 6, which electronic configuration is correct? Titanium has a configuration of argon for S2, so if it is 2+, it's going to be just argon, so this is wrong. For chromium, it has a configuration argon for S1 3d5, so this one here is also going to be wrong. For iron 3+, if you look at the configuration of iron, it's argon for S2 3d6, but if it is iron 3+, it should lose the 2 s electrons or the 2 for s electrons, and then 1 electron from here to give us a 3d5, so that is out. And lastly, copper. Copper has a configuration of argon for S1, 3d10, so this is going to be the answer. In question 7, the structure of the complex we see here is shown. They say, what is the coordination number of chromium in this complex? 1, 2, 3, 4, 5, 6. Each has 6 dative covalent bonds, so we can say each chromium ion has coordination number 6, and C should be the answer. In question 8, which complex contains only monodentate ligands? When we look at A, iron has coordination number 6 and there are 6 ligands. It means Cn is a monodentate ligand. If we go to B, chromium has coordination number 6, but we see there are 3 ligands. Therefore, this is going to be a bidentate ligand. Here we have nickel, which has coordination number 6, but there is 1 ligand, and that means EDTA is hexadentate. And in cobalt, still coordination number 6, but we have 2 of these, each is bi, and 2 of these, each is mono. So here we have a combination of mono as well as bi. So the correct answer should be A. Moving on to question 9. Which complex has a ligand-metal ligand bond angle 109.5? The bond angle 109.5 exists in tetrahedral structures. So here we can see it's going to be CuCl4. If I draw, it's going to be Cu. We have 1, 2, 3, and that is going to be the complex. And then we put square brackets and the charge outside. That is going to be tetrahedral, so the answer should be A. In question 10, which ion is not blue? Vanadium 4 oxide is going to be blue. Hexa aqua cobalt 2 is pink. Hexa aqua chromium 2 is going to be blue. And hexa aqua copper 2 is also going to be blue. So we can see it's only B which is not going to be blue because it will be pink. Which equation shows a redox reaction in which the solution turns yellow? We can see this is not going to be the case because here we create a green solution. This is still the same oxidation state, so we cannot call it a redox reaction. When chromium 3 plus reacts with hydrogen peroxide in alkaline conditions, oxidation will occur, forming chromate 6, which is going to be yellow. So the answer is going to be D. Here we form a yellow solution. And in question 12, aqueous ammonia is added in excess to an aqueous solution of copper 2 plus. What is the equation for the overall reaction? When we add excess aqueous ammonia to copper 2 plus, a ligand substitution reaction is going to occur. We'll form this complex, and so this is going to be the equation for that reaction. And in question 13, which equation shows the formation of a precipitate? We have zinc hydroxide reacting with the hydrogen ions that are present in this ion, and then forming this compound here. This is going to be a white precipitate. However, the other reactions we see here, there is going to be excess of further deprotonation, like in this case, that will lead to a soluble solution. And in this case here, we can see still, this is going to be soluble and that is going to be soluble. So this is the only precipitate that is going to be formed, which is going to be white, and so A should be the answer. In question 14, what is the sequence of oxidation number changes for vanadium when vanadium pentoxide is used in the contact process? In the contact process, sulfur dioxide reacts with oxygen to produce sulfur trioxide. This reaction is catalyzed by vanadium pentoxide. When the two-step reaction occurs, vanadium pentoxide will react with the sulfur dioxide to give us sulfur trioxide and vanadium 4 oxide. And then later, this vanadium 4 oxide will react with oxygen to form vanadium 5 oxide. So it's going to be vanadium 5 to vanadium 4 and then 4 to 5. So C should be the answer. In question 15, what is the total number of delocalized electrons in this compound here? I try to draw it for you here, but the key thing is even if you do not draw, the number of delocalized electrons are going to equal to the number of carbon atoms that are present, because each carbon atom contributes 1 electron to the delocalized system if we see the structure here. So since there are 14 carbon atoms, each is contributing 1 electron, there are going to be 14 electrons that are delocalized in total, and therefore C is going to be my answer. In question 16, which statement explains why bromine reacts more readily with phenol than with benzene? If we look at phenol, there is oxygen and hydrogen attached, and the lone pair on oxygen is going to be incorporated into the ring. This makes the ring more susceptible to attacks by electrophiles. Even weaker electrophiles can attack it, like bromine. But with benzene, we will need a halogen carrier in order to create a strong electrophile. for the reaction to occur? So the answer is C. A lone pair of electrons on oxygen in phenol is delocalized into the ring. This makes the ring more susceptible even to be attacked by weaker electrophiles like bromine, while with benzene, like I've already said, we'll need a halogen carrier creating a stronger electrophile for the reaction to occur. In question 17, which reaction can form a secondary amine? So in the first one, of course, there is a carbon here. This is reduction. We're going to produce CH2, NH2. This is a primary amine. When we go to this one, since there is a lone pair here, this lone pair is going to be donated to one of these carbons, and then the bond between the carbon and the Br breaks, creating some structure like this. And when this hydrogen goes away, we will remain with something like that. That is going to be a secondary amine. Since we already have a secondary amine here, a reaction taking place is going to produce a tertiary amine, and there is a possibility of quaternary salt. So the only possible answer is going to be a B. In question 18, compound X reacts with excess nitrous acid followed by coupling with excess phenol to form an azo-dye. And again here they've said excess so that the NH2 is completely converted into that. We can see there is that and that. So all these are going to be converted into something which is similar to that. They say what is the structure of the azo-dye? If this is reacted with excess phenol, it means there are going to be phenol groups attached here and there, producing a structure similar to this. So here is going to be my answer, is the only thing that makes sense based on the information that is given. In question 19, for amino acids are dissolved in the ionized water to form separate 0.05 mole per decimeter cubed solutions, which amino acid will give the solution with the lowest pH? So solution with the lowest pH is going to be a solution where more hydrogen ions are lost in solution. Since we have two carboxylic groups here, more hydrogen ions are going to be lost in solution, and this is going to cause the lowering of the pH in comparison to the others. Here we have one carboxylic group, here we have one, and here we have one. So there is going to be higher hydrogens lost here. And if we look at the other parts of the compound, we have one NH2. So if we lose one hydrogen here and it goes here, at least there is another hydrogen that can be free. Here we can see one carboxylic, one amine, so that could be used up. Here too it could be used up. And here we'll actually need more. So this is going to be the best one at causing a lowering of the pH. In question 20, which carbonyl compound a Grignard's reagent would not react to form compound Y? Looking at this compound, this is a tertiary alcohol. To produce a tertiary alcohol using Grignard's reagent, we will need to use a ketone and then Grignard's reagent. So since here we're looking for something that will not, it means we're looking for something that is not a ketone. So we see this is an aldehyde, this is a ketone, that is a ketone, and that is a ketone. So the aldehyde is the one that is going to be ruled out, and therefore A is going to be my answer. So this brings us to the end of section A. Let's continue to section B. Question 21. This question is about mercury and its compounds. Mercury is a liquid element in the same group of the periodic table as zinc. The electronic configuration of mercury is given here. Mercury forms compounds in either +1 or +2 oxidation states. Explain why mercury is classified as a d-block element but is not a transition element. It's a d-block element because its outermost electron is going to be filling the d orbitals. However, when we look at the configuration of mercury, we can see it does not form stable ions with partially filled d orbitals. Since they told us it forms +1 and +2, Mercury 1 is going to have a configuration like this, which is going to be 5d10, and Mercury 2 plus has a configuration which is that. So I said mercury is a d-block element because its last electron fills the d-block, or you would say its last electron fills the d orbitals. However, H plus and H2 plus have no partially filled d orbitals, so electron transition does not occur. In part B, mercury reacts with nitric acid to form an aqueous solution of mercury nitrate, a nitrogen monoxide gas. The unbalanced equation is shown, so this is the equation. And then they say explain using oxidation numbers why this is a redox reaction. So this is a redox reaction because mercury is converted to mercury 2 plus, that is oxidation. And here in nitric acid, the nitrogen is converted from +5 oxidation state to +2 oxidation state, and that is reduction. So because both oxidation and reduction occur, we can call this a redox reaction. And down here they say deduce the ionic half equation for this reaction. State symbols are not required. So I wrote down here from mercury we get mercury 2 plus, so it means 2 electrons are going to be lost for that oxidation reaction. We can see from that to that. And then for the reduction reaction, the oxidation state of nitrogen here is 5 and this is plus 2, so we have to add 3 electrons here to balance. And after that, the other side we have to add oxygen because here we have 3 oxygen atoms. I have to create 3 as well the other side. So since I have only 1 here, I put 2 waters to balance the 2 oxygen atoms that are required. And that means now we have 4 hydrogens on this side. We need to create 4 hydrogens here as well. Since here we have 1 hydrogen, I will add 3. In the end, we'll have something similar to this. The 3 hydrogens here, the 1 hydrogen here create the 4 hydrogens, and then the NO3 minus, and then the 3 electrons, then NO the other side and water. So this is the balanced equation I wrote here. And down here they say complete the equation for this reaction by adding the stoichiometric coefficients. To write the balanced equation, we have to look at the 2 half equations. Since here we have 3 electrons and here we have 2, we have to balance those by multiplying the oxidation equation by 3 and the reduction equation by 2 to create 6 electrons for each half equation. So in the end, we will have 3 mercury, which is this, and this is also going to be 3. And multiplying this equation by 2 is going to leave us with 8H plus, or you would say 8 nitric acid. And then the other side, we're going to have 2NO, and then we'll have 4 waters, as we can see here. So these coefficients are going to be easy to get if you can balance the electrons for the 2 half equations before you combine them together. Moving on. In part C, mercury 2-fulminate is an explosive. It is produced in the reaction between that and ethanol. The other products of the reaction are ethanol and water. They want you to write the equation for the reaction of 1 mole of mercury nitrate with ethanol to form mercury 2-fulminate. State symbols are not required. Since mercury 2-fulminate is produced, there is water produced as well as ethanol. These are the products formed, and on the other side, they say it reacts with ethanol to give us this. So just balance the equation. That is going to be easy to do. The next part says mercury 2-fulminate decomposes as shown. We can see the equation for the decomposition. Calculate the total volume in centimeters cubed of gas produced when 1 gram of mercury 2-fulminate decomposes at room temperature and pressure. If the decomposition occurs at room temperature and pressure, we can call this the molar gas volume, sometimes called Vm, is equal to 24 decimeters cubed per mole. I began by finding the molar mass of mercury 2-fulminate. We have 206 times 1. Then we have the carbon, which is 12, nitrogen, which is 14, oxygen, which is 16 times 2. Adding everything up, I got that in gram per mole. Then the moles of mercury 2-fulminate are going to equal to mass divided by molar mass. This is the mass, and this is the molar mass. So I got these as the number of moles. However, carbon dioxide is produced. The moles of carbon dioxide produced are going to equal to 2 divided by 3. I'm using the moles of mercury 2-fulminate to get the moles of CO2 produced. So 2 over 3 times the moles of mercury 2-fulminate, since the ratio is 3 to 2. And these are the moles of carbon dioxide produced. So then the volume of gas is equal to number of moles times molar gas volume. The number of moles is going to be what we have here times the molar gas volume. Here I use the molar gas volume in centimeters cubed per mole, not decimeters cubed per mole like here. And then I got 56.2192 centimeters cubed. Since equal volumes of gas at room temperature and pressure will occupy the same volume, it means I can use the mole ratio as the volume ratio. So if 56.2192 centimeters cubed are for carbon dioxide, that of carbon monoxide is going to be the same, and that of nitrogen is going to be the same because it's the same number of moles. So adding everything up, I got 169 centimeters cubed to 3 significant figures. In part D, mercury 1 chloride, which is also known as calomel. A saturated calomel electrode may be used as an alternative to the standard hydrogen electrode. And down here they say the half equation for the calomel electrode is what we see here. They say the standard electrode potential of the calomel electrode is given. Suggest why potassium chloride crystals are needed in the outer tube of the electrode. These are required because, of course, potassium chloride will decompose fully, producing potassium ions and chlorides. So this is going to be required to provide chloride ions continuously in order to maintain the concentration of Cl-. Next they say, a calomel electrode was used to measure the standard electrode potential of tin 2 plus tin half cell. And they say the reading on the voltmeter in this cell was plus 0.37 volts. Deduce the standard electrode potential for the SN2 plus SN solid half cell. E theta of a cell is equal to E theta right minus E theta left. So they've given us 0.37. 0.37 will equal to 0.24, which is provided, minus the E theta for the left. So E theta for the left is going to be 0.24 minus 0.37, giving us negative 0.13 volts. And again, 0.24 is the electrode potential of this calomel cell. And down here they say write the overall equation for the cell reaction. We have the tin-tin-2 half cell equation, and then we have the calomel one. So I follow the electrodes. Since this is going to be oxidation, this is going to be reduction, we just combine the two, ensuring that the electrons are the same and they're cancelling out. So that plus that gives us that plus that and that, which is what we see here. And in part 4, add labels to complete the diagram in a standard hydrogen electrode. Include details of any essential conditions. In a standard hydrogen electrode, gas is going to come in here, hydrogen gas. It's going to be at 100 kilopascals. And then this electrode is going to be a platinum electrode. This solution is going to be 1 mole per decimeter cubed concentration, and it's going to be made of acid, for example, hydrochloric acid. The other condition is a temperature of 298 Kelvin. And then they say suggest one advantage of using a calomel electrode in place of a standard hydrogen electrode when measuring a cell potential. The difference here is we have no salt bridge, so that is going to be advantageous. So this brings us to the end of question 21. Let's continue to question 22. In question 22, the amount of calcium ethane dioate present in a sample of spinach is determined by redox titration. 11.4 grams of spinach leaves are stored in 50 centimeters cubed of a warm acidified solution of 0.01 mole per decimeter cubed, potassium manganate 7, oxidizing all the ethane dioate ions. So this is the equation for the reaction. They say the excess manganate 7 ions are then titrated with an acidified solution of 0.05 mole per decimeter cubed and 2 sulfate. Again, we see the titration equation is here. They say 25.95 centimeters cubed of iron 2 sulfate solution was needed for complete reaction. Calculate the percentage by mass of calcium ethane dioate present in the spinach leaves and give your answer to an appropriate number of significant figures. So I began by calculating the number of moles of iron 2 sulfate because we can see this information here from the titration. So number of moles of this is equal to 0.05, which is the concentration, times the volume. I divided by 1000 to convert the volume from centimeters to decimeters cubed. And these are the number of moles. These are moles of iron sulfate that were reacted. Then I used the moles of iron 2 sulfate to give me the moles of manganate. The moles of manganate are going to be 1/5 times the moles of iron 2 sulfate, since the ratio is 5:1. So when I divided that by 5, I got 2.595 times 10 power negative 4 mole. These are moles of manganate that were left from the first reaction. The initial moles of manganate, again using this information, they were the concentration times the volume in decimeters cubed, giving me that. So that means to find the moles that reacted, it will be the initial moles minus the moles that were left in the first equation, because the moles that were left are the ones that were titrated. So this is what I did here, and I got that. So these are the moles of the manganate that reacted with the ethane dioate, meaning moles of ethane dioate are going to be 5/2 times the moles of the manganate, because we can see the mole ratio is 2:5. So that gave me 6.0125 times 10 power negative 4 mole. And so the mass of calcium ethane dioate present is going to be number of moles times molar mass, which is this moles, times the molar mass we calculated, which is 128.1. And that gave me this in grams. So the percentage by mass should be the mass of calcium ethane dioate divided by the initial mass of the leaves times 100. And I got 0.676% to 3 significant figures. So this brings us to the end of question 22. Let's continue to question 23. In question 23, some thermochemical X-ray diffraction and bromination information on benzene and cyclohexene is shown. So we have the thermochemical data. Enthalpy change of hydrogenation of benzene is negative 208, and that of cyclohexene is negative 120. Of course, the Kekulé should be negative 120 times 3, giving us negative 360. And then down here, they give us the X-ray diffraction data. You can see here, they are all the same. These are the same. That and that are the same, and this is different. This is because the carbon-carbon bonds in cyclohexane are different, while the carbon-carbon bonds in benzene are exactly identical. Then from bromination, we can see for benzene, we'll need a halogen carrier, and then bromobenzene is going to be formed. For cyclohexene, there is no heating, just at room temperature, and we form 1,2-dibromo cyclohexane. So here they say explain how all this information provides evidence that the electrons in the pi bond of benzene are delocalized. My answer included information discussing all the points above, so I said based on thermochemical data, the enthalpy change of hydrogenation of benzene is negative 208 kilojoules per mole, but that of 135 cyclohexa triene would be 3 times negative 120, which is negative 360 kilojoules per mole. This is the would-be theoretical Kekulé structure. So benzene is more stable by positive 152 kilojoules per mole. Based on X-ray diffraction, all carbon-carbon bonds in benzene have the same bond length, which is given. However, the carbon-carbon single bonds and the carbon-carbon double bonds in cyclohexene have different bond lengths, and that is, considering this is 139 and these are different. I say the carbon-carbon bond length in benzene is 139 pm, which is between the carbon-carbon single bonds and the carbon-carbon double bonds, respectively. Based on the bromination reaction, benzene reacts with bromine through an electrophilic substitution reaction mechanism. A halogen carrier, which is that, and heating are required because the delocalized pi bond electrons are less reactive. They need stronger electrophiles for the reaction to proceed. However, cyclohexene reacts with bromine through an electrophilic addition reaction mechanism. The electrons in the carbon-carbon double bonds repel the electrons in the Br-Br bond. This creates the Br sigma plus, meaning a partially positive Br, which then receives electrons from the carbon-carbon double bond, so the reaction is going to proceed faster. So this brings us to the end of question 23. Let's continue to question 24. Question 24. This question is about polymers. There is PAM and PAA are water absorbent addition polymers. We can see them here and that. PAM is made from acrylamide monomer, which is given here. They say give the IUPAC name of the acrylamide. If we look at the main chain, it has 3 carbons, but there is a double bond, so it's going to be propene. It is also an amide. And since the double bond is on carbon 2, since this carbon should be carbon 1, it's going to be 2-propene amide. Next, they say explain why PAM is able to absorb large amounts of water. They want you to include a diagram in your answer. When we look at the structure PAM, there is a lone pair here, and there are lone pairs on oxygen. And if they interact with water, there is a chance to form intermolecular hydrogen bonds, as we can see here. So I said, PAM can form multiple intermolecular hydrogen bonds with water using the H on NH2 and a lone pair on oxygen in the carbon-oxygen group. The next I say the structure of PAA in aqueous solution is pH dependent. Below pH 4, the structure PAA is compact due to the formation of intramolecular hydrogen bonds. We can see it here. Above pH 8, PAA has an open coil structure, which we can see here. This suggests why PAA exists as an open coil structure above pH 8. Of course, above pH 8, the hydrogen ions are going to be lost, and this is going to create a COO- structure. These negative groups will form components in the PAA, which repel each other, and this is going to create an open structure. In part B, PVP is an addition polymer used in the pharmaceutical industry. The average molar mass of PVP is 90,000 grams per mole. We can see this is a repeat unit. Draw the structure of vinyl pyrrolidone monomer used to make PVP. So the monomer is going to contain this part, that part, and a double bond between here, excluding that bond and that bond. So this is what I drew here. Next, they say calculate the number of monomers needed to make 1 molecule of PVP polymer with a molar mass of 90,000 gram per mole. I want you to give your answer to the nearest whole number. So I got this structure here, exposing the carbons and the bonds that are linked to hydrogen so that I can get the specific molecular formula. We have 1, 2, 3, 4, 5, 6 carbons. And then the hydrogens are going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. I included hydrogens, keeping in mind that each carbon should have only 4 bonds around it. Then there is 1 nitrogen here and 1 oxygen. So this is going to be the molecular formula. So the molecular mass of the monomer is going to be carbons, which are 6 times 12, plus 1 times 9, plus 14 times 1, plus 16 times 1, giving us 111 gram per mole. So since this is the molar mass of the monomer, the number of monomers is going to be the molar mass of the polymer divided by the molar mass of the monomer, giving us 811 monomers. A 740 milligram tablet of a painkiller contains 4% PVP by mass. Calculate the number of molecules of PVP polymer in the tablet. The mass of PVP in the tablet is going to be 4 divided by 100 times the total mass of the tablet, which is going to be 29.6 milligrams. If we divide this by 1000, we convert it to grams, which is 0.0296 grams. The number of molecules will equal to the mass divided by the molar mass times Avogadro's constant, which is 0.0296 divided by the 90,000 times Avogadro's constant. And this gave me that, which is approximately 2 times 10 power 17 molecules, rounded off appropriately. And in part C, all types of nylon are condensation polymers. State what is meant by the term condensation polymer. It's a large molecule formed by reacting many monomers with lots of small molecules like water and HCl. Next, they say the structure of nylon 6,6 is shown. Again here, first ignore the carbons are included. They say nylon 6,6 is made from 2 monomers. Deduce the structure formally of these 2 monomers. This is where we have the amide, so I can break the bond from here by carrying out hydrolysis, add OH to this carbon, and add a hydrogen to the other side. Then also add OH to this carbon and add a hydrogen this side. So the carboxylic part is going to be the first one, or the dicarboxylic acid, and the other is going to be the diamine that remains. Next, they say caprolactam can be directly converted to give a different polymer, nylon 6, in a ring opening polymerization reaction. They say draw 2 repeat units of nylon 6. When this ring opens, we can see this part is going to be connected here. Then we have 1, 2, 3, 4, 5 carbons, which is going to be 1, 2, 3, 4, and 5. And then the NH, and then another repeat unit since we are drawing 2. So these are going to be the 2 repeat units all the way. And that will be my answer. So this brings us to the end of question 24. Let's continue to question 25. Question 25. The synthetic drug of the cane family are used as local anesthetics. Cane drugs prevent nerve activity by binding to sodium channel receptors in the lipid cell membrane of neurons. So we have these specific structures in the cane family. They say name 3 functional groups present in benzocaine. If we go to benzocaine, which is here, we have an amine or primary amine. We have an ester, and then we have a phenyl, which is a benzene ring. So those are the 3 structures present. And next they say procaine can react with hydrochloric acid to form a monohydrochloride salt. Write an equation using molecular formulae for this reaction. State symbols are not required. If I go back to procaine, this is the molecular formula of procaine. This is reacting with HCl and a salt is going to be formed. The next they say explain by considering both nitrogen atom in procaine which nitrogen is more likely to be protonated in the reaction with hydrochloric acid. This nitrogen is going to be more likely to be protonated in comparison to the other. In this NH2, the lone pair of nitrogen is incorporated into the ring, not readily available to be attacked or to receive electrophiles, while this, its electron density is going to be increased because it's connected to electron donating groups, so it's going to be more susceptible or easily attacked by electrophiles. So I say the nitrogen in this group, which is that nitrogen, because it is bonded to alkyl groups that are electron donating, they're going to increase its ability to act as a base. The nitrogen, which is in the NH2, is attached to the ring. The lone pair on that nitrogen is incorporated in the ring, so the electrons are not readily available to be donated. In part C, when benzocaine and procaine are hydrolyzed, one of the products formed is the stem in both reactions. They want you to give the structure. This is going to be the structure if I take you back. Hydrolysis is going to produce a carboxylic acid and a carboxylic acid because both of them are esters. So a carboxylic acid is going to be the answer, this carboxylic group. And in part D, lidocaine can be prepared in the synthesis shown. We can see it here. They say give the mechanism for part 1. In part 1, this is nitration. Concentrated sulfuric acid and concentrated nitric acid are going to form a strong electrophile, which is an O2+. So the formation of the electrophile is occurring here, and this electrophile will receive electrons from the ring, creating that, and then the carbon-hydrogen bond is going to break, creating what we see here, and the hydrogen is lost. Actually, in the end, this is going to combine with that to regenerate sulfuric acid, which was acting as a catalyst. Next, they say a low yield of 2,6-dimethylnitrobenzene is obtained in step 1 due to the formation of additional organic products. Give possible structures for 2 additional organic products. Of course, there is a possibility of further nitration, and the other nitration products could be that as well as that. In part 3, they say give the reagents for step 2. This is reduction. It's going to be tin in concentrated hydrochloric acid. The next part says deduce the skeletal formula of the reagent in step 3. Again, to go back, step 3, because we see this nitrogen is going to be attached to a carbon in the CO double bond. So that means there is going to be a halogen that comes, and this is going to be a substitution reaction. So it's an acyl chloride on the other side, but there is also chlorine on this side. And down here they say state the type and mechanism of reaction occurring. It's a substitution reaction, and there is a nucleophile, Cl, that is going to be replaced by NH2. In part E, adecane is a chiral molecule. Indicate any chiral centers on the structure of adecane. This is one chiral center iso, and again remember chiral center is a carbon which is attached to 4 different groups. There is a hydrogen here, a CH3, then there is this group, and that group here, so they are all different. Next, they say adecane is metabolized in the body with a half-life of 20 minutes. A patient is given a dose of 100 milligrams of adecane. Calculate the mass of adecane in micrograms remaining in the body after 4 hours. They say 1 microgram is equal to 10 power negative 3 milligrams. So I began by converting the 100 milligrams into micrograms and multiplying that by 1,000. I get 100,000 micrograms. Since the time is 4 hours, 4 hours is 4 times 60, which is 240 minutes. So for this, the number of half-lives is going to be 240 divided by the 20 minutes, which is going to be 12 half-lives. The mass remaining is going to be the original mass times half for the number of half-lives. 100,000 times 1 over 2 power 12, which is 24.4 micrograms, and that is going to be the mass remaining. So this brings us to the end of question 25, as well as to the end of the whole paper. Thank you for being with us. Do not forget to subscribe. See you in the next video. Bye-bye.